Pinball, and let's hit the microphone on.
My name's Joe Zankus, and I started working with Fast maybe 6 months ago.
And what's so great is Aaron's had a very long relationship with Joe, and really I have been working virtually with Joe almost the entire time, just over PC on meets and all that kind of stuff. So it's awesome to finally really hang with you in person. So thanks for
For
being
sure.
here. So what we're here to talk about today is machines making machines. It's kind of an interesting topic, and I guess we probably should have given a little bit more detail on what that really was. But we've been, as we've been growing and getting into some production machines, it's like the old days of Aaron just sitting at a bench and hooking up an emulator and programming code in and looking at a meter and stuff like that. Those days are long behind us. So we had to make a lot of interesting decisions at Fast on what we want to do to scale our production line as things move forward. So this is kind of the story a little bit about what it's like to manufacture in the field or just manufacture boards in general, and kind of our journey on how we got to where we are today. So to get started, when I first started my career, I worked at a company called Date.io. And this is a company that makes equipment that programs all kinds of parts, processors, EEPROMs, all that. And since these are used in things like aircraft, traffic lights, and all that, we had to make sure that all of our equipment was, it's the ones on the very right, I could hear it's a little, thank you, Yomoto. So we had to make sure that every single one of our equipment worked perfect. So it's like we needed to get some of the most expensive test machines out there that do 100% functional tests on what we were shipping. So a traditional test machine like this, at the time that I worked there, they were about $300,000 a piece. And what this is essentially oscilloscopes, meters, everything is embedded in that bed of nails that you see on the right of this machine over there. I don't know, does my mouse, I guess it does work right there. So this right here is a big, hold on one second. Test, test, test.
That's good.
Okay, is that, okay, I think we got it now. So based on how many pins that you're going to be testing, so each one of these little contacts that are on here can test one point. So you have a whole bunch of equipment tied to that one test point, but you would have to make fixtures to sit there and make that test point go where you want in your circuit. So this is where the money comes in. Like, obviously a contract manufacturer probably owns that machine, but you would have to make the test fixture that goes into this. So you're not paying the $300,000 development, you're paying for a $20,000 to $30,000 development to make this. So what happens, the one on the left here, all those pins that come out of the machine come up to some boards, and then you typically would wire wrap and then come into what your test fixture looks like on the top. And on the right hand side, you'll see a couple of fixtures that have some points that would come down and press the circuit board into those bed of nails, and then the test would go. Now, for us, we finally hit, I think we're around 80 unique boards now at Fast Pinball. Even if we had to do 20 of them in volume at $25,000 a pop, that's a $500,000 investment. Even though these machines are still used today, it's like they're pretty expensive to run. So it was kind of like, even though this is my past, I didn't think this is what we could do going forward. But just to give a couple of pros and cons about this type of test fixture, the part I love is that it's high fault coverage. You can achieve 100% functional test because not only can you test all the components and what their values are with meters and all that kind of stuff built into that equipment, but you can also power your product up and do a functional test to make sure that it actually does operate. It's very rapid. Once you have that fixture go, you just pop a board in there. It does the test in seconds. So great for high volume, and being a high mix, low volume company, this doesn't really suit us very well. And then it's going to detect shorts, opens, missing components, and some analog behavior. Anyway, cons, very expensive fixtures, long lead times for those fixtures to be done, not ideal for our mix of products, and obviously every time you turn the board and something changes or moves, you're up to either modifying that fixture or making a new one. So a lot of our boards are tested using flying probe machines, and this is one of my favorite machines ever. It is so fun to watch. Like, what happens is those probes that you see on the right-hand side, it almost reminds me of a spider coming down, and these probes are moving in XY gantries and can go probe the finest components, you know, O2, O1 resistors, you know, almost like grains of sand. The resolution on these machines are fantastic. And you know, they do a great job. They can't really do functional testing like the board powered, but you can check almost every single connection that a board has to make sure that there's no shorts, no opens, you know, board's good, part's good. It's a great test. However, you can imagine with all of these probes going all over your board, it's incredibly slow. And the machines were around the same price, around $250,000 when they come back, but on the used market, you know, you can pick them up for $20,000 now. So there is a lot of them out there, but it's like they charge per time on how long it takes on the line. So for us, again, even though some of the contract manufacturers have this, it wouldn't be worthwhile for us to try to spend the money that it would take time-wise to test all our boards on this. So the flying probes machines, no custom fixture needed. I mean, you pretty much just give your Gerbers and a few other things to the machine and it's ready to go. So super fast setup. You can test bare boards. The nice thing is most of the board houses have these, and the boards that we get actually are tested by these. And I don't know that they do it 100%, but they do enough that they can tell if there's a manufacturing problem. But it detects open shorts, components presence, orientation, all that kind of stuff, but it does not do functional testing natively. Some of the cons: slower than the Benells, limited test coverage. Occasionally then you have to be realigned to make sure they're touching the points you know, correctly. And obviously it adds quite a bit more to the manufacturing cost because machine time, you know, sometimes it's the slowest machine in the entire manufacturing process. So most of the contract manufacturers we deal with do have optical inspection, and so this is using high resolution cameras. It'll go down and inspect all the solder joints, see if parts are lifted. It's actually pretty good. It's not very expensive, but the coverage is not very well. And so it's fast and automated, ideal for high volume, great at catching solder defects, missing parts, misalignments, all that. Non-contact, doesn't require a custom fixture. But again, it's not doing a functional test. So for us, we could not take these boards and just send them right out to our customers or to our partners. So it's great for what it is. Sometimes it's good to do just to see how the manufacturing process is going, but it's nothing that we'd want to do like long term. So visual only, can generate false positives, negatives, expensive upfront costs, anyway. So over the years, Fast Pinball has learned some hard lessons already. You know, the part shortages, we were actually pretty proactive during COVID, and we actually bought a lot of parts before we knew it was coming, and so we bought a lot of surplus. But some parts we thought would be very easy to get, like DC to DC converters. All of a sudden it seems like we were out almost a year on that part. So we actually had to change to other parts, and since we used it on so many designs, we were forced to change and roll almost every one of our common boards. So that was a very painful lesson. We now keep quite a few of those in stock all the time because we know how important it is. And we did have one batch that had counterfeit parts. It was this crazy 6-pin device. It's one of our smallest components. It has 3 diodes in one package. And we got the boards back from our manufacturer and we started testing them, and they didn't work at all. And this is all of our switch inputs on all of our boards. They all go through diodes first. And someone duplicated the part and they put the pin 1 marking on the wrong side. So they were rotated 180 degrees. I figured if you're going to counterfeit something, I could see it being a little off, but being rotated 180 degrees and have the pin 1 marking on the wrong side, that was a bit much. And so we were kind of in a hurry to get that batch out. They ran it for us really quickly, and it was a shame because there was no good way to replace them. There's so many of these on the board. We had to saw them all in half, show them the pictures. They covered it 100%, but wow, that was, someone paid the price for that one. And then we also had one other established product that we had, that one of our diodes was turned around 180 degrees. I don't know if anyone in here had that problem, but we sent out some power supplies and we told our users to how to do it. A lot of them tried to even though it was a service mount component, rotated themselves, but a few people sent them in, and so a little embarrassing on that one. So in the beginning, this is, I didn't have a good picture of Aaron doing this, but this is pretty much, Aaron pretty much inspects everything before it goes out, and you know, almost all of our boards that are keyboards have a processor in one way or another that needs to be programmed. So we were using the off-the-shelf tools made by that manufacturer to program that specific part. And so we would have to sit there and plug that in somewhere on the board, measure some voltages, hook it into a system to see if that was actually working. So this is kind of what our experience was like in the beginning. When we start getting into production, like one of the first products we got into production with was the, or high volumes, was the Funhouse 2.0 kit. And so that's a WPC89 board. And obviously we don't plug this in a pinball machine each time. We did a couple of them where we did plug it in a machine and play it, but we weren't going to do that with every single board. So anyway, we decided to make some type of dex fixtures. They were kind of crude. Here's that actual board that I'm holding up right now. And so you can kind of see these appendages. I think we all pretty much know what the WPC89 board looks like, but you see these appendages on there. And in the right photo, you can see that there's a ton of LEDs, like that entire array. This is the switch matrix, all the switches in there, or no, yeah, all the switch matrix are in this one, and all the drivers are represented by LEDs across the top. So what we would do is send out test patterns, and we would visually see, based on an LED just kind of moving from left to right, that all the drivers are okay. And we would do kind of a wig-wag pattern, putting an X on all the rows and columns. Sorry, actually not switch matrix, that was a lamp matrix. So 64 lamps are represented by the LEDs there, and so we could see what the pinball machine was trying to do with our test code running that lamp matrix. So that worked pretty good. It got all of our Funhouse 2.0 kits out there. And but we needed, when we started to get into more volume with some other boards, we started to try to make our second generation program and test station. So you can see it on the screen there, but there's also, you can come by later and take a look at this. But that bottom right corner button where it says select board, it's great. You hit that and it will come up with all the different products we can use on this. You select that. You still have to put some cables and key parts of the product to program it and test it, but this is kind of like what we're using today. So somewhere, I don't know, when did you and Aaron start talking about all this test fixture stuff? Because I was kind of in a vacuum on that.
Yeah, so the funny story is there's some home brewer that was like, I bought a bunch of this stainless, like I have too much. Does anybody want some? I'm like, well, of course I do. I want to get back into my project. And then I think he was in Seattle somewhere. I'm like, oh, but it's so far. And then he's like, well, it happens that Aaron from Fast Pinball wants some. And I'm like, well, can I just stop at his house? He's like, yeah, we'll figure something out. I'm like, oh, perfect. Like I get my in of like talking to him and just see his stuff and see if I can help with whatever he's working on. And then he's like, well, I hurt my hands because every board I got to sit there and put these connectors in. I'm like, that's terrible. Why are you doing this? And so my background, so I'm a mechanical engineer, but I've intertwined into electronics depending on what job I was at. And I've had a little experience with, they call them pogo pins, so they're these little pins that are spring-loaded and that contacts with all the pins. So I'm like, well, okay, I've never really made one, but I know I could do it. So the way I started was, so he sent me the boards, and so I 3D print everything because I have 3D printers. I've worked with them forever. So my first idea was, okay, we'll put the board in here. I'll have some angled walls, so you just kind of drop it in, and then you've got this hinge thing that comes down. Here's all your contacts to kind of like put pressure on the board. And so I did this, and it's like, well, it's not really lining up, so I made a little bit more changes. And then he's like, well, the way we do it, or the industry does it, is everything is vertical, so you're not trying to like bend over and push these pins down. So I ended up building that because I'm very much like, I don't want to spend money. Like if this doesn't work out, I put minimum amount of investment in. And then he's like, well, let's just buy this thing because this is on Amazon for like 150 bucks. I'm like, well, here's the issue. When you buy a fixture, you have no dimensions whatsoever. So you're basically reverse engineering whatever they built here because you need your origin point, because if you don't know where you're starting from, you don't know where everything's lining up. Like I don't know the distance from these two posts to wherever these screws are. So you measure as close as you can get to it, but you're talking about pins that are literally, what, 0.1 inch pitch. So you're getting down to stuff that's pretty precise. So precision is very important. So I got this to work, and you could see, like, let's see, you can't see it, but like in one of these signs, I literally had to cut out this, I think it's ABS, but I had to really modify this box to get this to work. So, but I got to work, this functions. And then I ended up building this. So the nice thing about building from scratch, there's a few things. One, all this is in SolidWorks, so I know what my references point is. I can make it the way I want it to. So like you can see here, what's really nice about this, you take two knobs off, and this whole bottom piece just comes right out. So if you ever need to swap stuff out, this is also 3D printed, so this comes off. So everything is very modular. These are the posts that like push down. So like he's talking about, you know, we're gonna end up doing it for every board. So this bottom board stays there, but this can get swapped out. And granted, there's only one board that's designed right now, but I'm working on the others. So this would pop out, and then whatever other board you have, this would be a different piece that gets swapped in. And the other thing that I realized is, so there's a thing called stack up. So originally I had pins up here, and when you talk about stack up means, okay, if I've got this board here, well, there's a little bit of looseness here, and then you got some looseness in this part, and then all that stuff adds up. So before you know it, you're where you think you are here, you end up way over here because everything moves a little bit. So the closer you get to whatever your part is to your test board, the better, because you have a less of a loop of where parts are getting aligned.
Yeah, so you probably can't see it here, but essentially the bottom board that's down here that you're looking at right now, that is the actual board that's performing the test. But you see what Joe did here is there's two steel pins that are tied securely to that board. So now this simple 3D printed piece right here is sitting on those same pins. So there's no stack up error because this is at the same.
Right, so these pins are in the same location on that board as whatever board you're testing.
And then to go one step further, when you actually put the board in that you want to test,
it's poking through.
Also poking onto those same pins. So
you can see them.
All three things are aligned.
You see the pins come through, and that means this thing's not going anywhere. And then you know all your pins are where you expect them to be from aligned to the bottom board.
And by the way, if there's any questions on any of this, I know it's a lot to go over, and it's probably very few people have ever seen a test fixture in their life. And so anyway, if you've got questions, please ask at any time.
Yes. I mean, it's not on there right now, but you can imagine this entire thing all making every pin contact all at the same time. And this locks in there, so you're literally, in a few seconds, you're throwing a board in, this is clamping down, and all the pins are making contact, and he's pushing a button, he's testing, versus connector, 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 and your hands are just getting destroyed because you're sitting there trying to get these plugged in.
So, it's what I love about the design and where we moved through all of these, because when we were doing the lid design, it's like the board kind of comes in sideways when you close the lid, and it was putting, it wasn't lining up quite properly because, the board is not aligned up on pins before you press it down. It's also putting undue stress on the pogo pins. But the way this is done now, and just those 3D printed pieces, there's nothing else besides the test board and the board under test that's unique to each fixture. So they're really just 3D printed parts holding everything else together. So what we're trying to do is make these low cost enough that they could be, not just at our facility, but other facilities as well, like our contract manufacturers. So let me go into a little bit here and show, what it took to get here, and then I'll show you a little bit of the CAD files that we did, that Joe and I shared, because like I said, first time really meeting in person for any significant time.
One other quick thing, so when we started this fixture was no big deal, and you're seeing now with tariffs, like the problem is either this is getting incredibly expensive, or China just will refuse to sell this. So now you have this problem where I can't get parts. We own this design. I can make all these parts locally, and we never have to worry about, we can't build fixtures because China doesn't want to sell us a part. So
So the way this started is, first off, we've been trying to do this already, but we created 3D models for all of our boards because a lot of our partners we're working with, if for their documentation and for doing all of their CAD layout, wants to see what our boards look like in their system. So we were already kind of proactively doing this, but you know, there's always the one model you don't have or whatever else. But when Joe got into the picture, it was so important to have every part because he's trying to go and put pressure points on certain points so that the board doesn't warp when it's getting all those pressure from those pogo pins. So it forced me to kind of like try to find all the models or make them up, what we didn't do, to at least get all the Z heights correct. But anyway, so that was the starting point in the CAD tool, was to, you know, take our existing boards. This is a 32/8 board, one of our driver boards, 32 switch inputs, 8 outputs. It's probably our most common driver board. And so that was our starting one, and that's what I did, gave him the step files. Next, what I had to do, and this was a really tough job for me because when you start testing boards, there's always the killer board. So what is a killer board? That's like for some weird reason 12 volts all of a sudden appeared on a communication line that's not supposed to have it, or your 3.3 volt processor and all that kind of stuff. Yes, when you power this board up, that board is going to die. But the worst part is that in certain cases, it might take out the test fixture too. So if you have 1,000 boards to do and all of a sudden your test fixture now is down, now all of a sudden you got a different problem. So I already try to make all the stuff that I do for fast very robust because I know who our market is. These are, you know, all you developers out there, some artists never touched hardware in their life. So I try to make it simple and robust enough that if you do something that's not quite right, it doesn't necessarily end up in smoke. And so, but now trying to make something that watches that to make sure it doesn't burn itself, it was really kind of a mind warp for me to try to solve this problem. So anyway, this one for the 32/8 ended up being 10 pages of schematics to sit there and get that all done. Every single one of our test boards has a RP2040 processor on it, so it has local functionality to administer the test. And then almost all our boards have some type of communication. So here's a page of communication, power supply with some current monitoring somewhere. I usually have one page that has all of the connectors on it, and this is the most important thing because I have to tell Joe where to go pick up all these test points and all that. And then we start to get into how we're administering the test. So normally if it's just an output, that's great. Here's a page right here using, this is what's driving all of our switch inputs. Well, normally these things are good for like driving like 500 milliamps, which a switch will never take. But if a switch is shorted at 12 volts, all of a sudden I got a problem now. So now adding things like resistors so that we can't overcurrent the fixture and destroy these drivers, you know, all that kind of stuff comes into play. So anyway, for such a simple board in a way, you know, 32 switches, 8 drivers, it ended up being 10 pages of stuff to make this all work. And so let me see, I believe I had that here. So here is the 3208 board, and then you can see the size of the fixture. I guess this is actually a different fixture, but they're almost all the same size. But anyway, just slightly larger. And you can see that there's almost no through holes on this anymore, where a lot of our boards have the through hole connectors. And the reason for that is all the points now that are going to be going up to the other boards have got like test pads that will be touching the pogo pins. So anyway, it's like we've tried different materials. We're doing a process called EING, which is a gold layer in there because all the pogo pins are gold. So we figured a gold to gold contact is going to give us the best contact and best longevity. So after the schematics were all complete, then I have to lay out the board, and this is the actual board that I wanted to show you for the 3208. When you kind of look at the footprint for this, you can kind of see the test points, how they kind of match up in there. This is where the all of the drivers come out, and then the 32 switch inputs are on all of these connectors kind of down at the bottom or wherever they're all, the traces are all going. So then the important thing is we're right back creating the step files for Joe one more time, because now he needs to have this board to sit there and line all that up. So, and you'll also notice, like, for each pin that we actually have to test, I put a little rectangular bar with a little arrow on it showing that, hey Joe, this is an actual place where we need a pogo pin. So how do you keep tabs of that? Because I don't, what do you do to go from here to make the 3D print?
Yeah, so when he exports a step file, you could pull that into SolidWorks. SolidWorks is I'm sure a lot of people know it's a 3D program, so all this was designed in SolidWorks. So when he gives me a board, I'm literally taking this thing and floating in the air, and I throw it on here, and then I with SolidWorks, the way you assemble parts virtually is they call them features. So like I would end up using these holes as my alignment, and I'd start putting in there. It would just kind of float here, but then I would know how to build something around that to attach this to whatever I'm building on there.
So I noticed that some of the blocks that you create, it's like all the pins seem to be here.
Yeah.
So on future models, like how are you to keep tabs of which pins we need?
I had thought about actually filling some of those in, so whoever's using it's very obvious. No, don't put they'll end up putting pins in every hole, and I think it'd be much better to just only have the holes that you need. So yeah, that's something I'm going to change on that.
So you probably are watching the cost more than that. Like how much does an individual pogo pin cost? These things do wear out with time. They do have springs in them. They are touching the boards all the time. They are plated. Stuff will wear off.
I think they're pretty cheap. I think it's like you get 100 of them for $10 on Amazon.
Wow.
So they're not very expensive. But
that's great. So anyway, if one does go bad, that's one thing that we're trying to do too. If we start seeing a couple boards in a row that have like, hey, switch number 23 is bad, it could just be that a pogo pin is not making contact as well. But Joe made all these things float. Like the amount of tolerance there is in there is tight enough to hold it where it needs to. But if a pin ever does go bad, I mean, you literally go in there with some tweezers or your fingers. Tweezers, if it's right next to it, like you said, the pitch is like really tight.
It is.
But if you need to remove one, they're super easy. Just pull right out of that 3D print and put a new one in there.
And like theoretically, like it's not shown here now, but there'd be pogo pins in between. Theoretically, this thing would sit on a shelf and it would never get removed. But even if you did, we talked about could we have some kind of like mid-layer where it kind of holds the pins. So because once you pull this apart, the pogo pins just kind of like all fall out. It's like dominoes. It's a mess. But you don't have to do that very often. It's only when you'd have to see if a pogo pin wore out.
Yeah, I found you learned pretty quick.
Yeah.
First time you dumped all the pins on your desk, you realize you don't want to do this again. So anyway, when we start making this, we start thinking about, how do we scale fast and like who are all these for? So obviously the thing that's burned us in the past is like with those reverse parts or the parts that were counterfeit. If we actually give these fixtures to our contract manufacturers, they could test them before we ever see them. And so that's going to be huge. So we're really trying to, Joe is keeping the cost of these so low. I mean, Joe, give us an idea, like how much mechanically does one of these cost?
Prices have fluctuated just because of things, and like I've already had to like resource parts because either they got horribly expensive or again, they just won't sell them. But I think this is probably under $200, which is pretty impressive, I think.
And since that can be used for a lot of boards, that's great. And then when you look at the cost of the only other thing we need is the bottom test board, and that's not much more than what our typical hardware is for the same board we're doing. Because yes, there's a little bit more components on there, but cost-wise, it's not that much. So if we can do these in enough volume, maybe like 25 pieces at a time, it gives us enough to test with, and then you give it to our contract manufacturers. And then also, we hope that some of our partners would want to get these as well. So if you're manufacturing a machine, you go put a board in and all of a sudden that board doesn't work, is it because your machine's wired wrong? Or is it because that board was actually bad? So we've had cases where, unskilled people that have not been, just start building the pinball machines have gone through multiple boards thinking it's the board problem when it's actually a killer machine that's killing the boards. So if they had some way to check to see if the board's actually good ahead of time, we wouldn't have that repetitive, cycle killing good boards. And then at some point in time too, we'd like to do like global partners where we could send test fixtures in other parts of the world and have consistent quality and manufacturing in other countries. So especially with things like the tariffs going on, all of that we won't have to suffer that as bad. And it just makes sense with shipping and all that. If we could make boards in other countries that have the same quality, then we don't have to have everything coming from here. So anyway, I think that's my last slide for this, so we can talk about this a little bit more. But yeah, so there's our newest program. The only thing I see here we haven't talked about is originally when we were very first start doing this, I was just putting a pass-fail LED in there. We were going to do all the stuff, flash some LEDs based on what the failure was. And one of the later additions was adding another RP2040 Raspberry Pi chip with an LCD screen up there and have a user interface that's common to all of them. So now we can get more specific, like, hey, Q7 is bad on this board or what have you. So that was kind of a nice addition, and I love that mount you made for that, Joe.
So I added a little knob. We have no idea if these fixtures are going to be on a desk, if they're going to be floating up here. So I kind of made like a little adjustability to change the angle, which is just a nice little feature. So
one other nice feature we did is we added a USB port on the top of that. And what that lets us do is change the code in that, plus the code on the test board. So if we decide that we need to speed things up or want to add an additional test that we had not done, we're able to do that as well in the future. So that was kind of future-proofing it a little bit. So with that, I don't really have much else on this. I'm open for questions if anyone has any questions, or Joe, if you have anything else that you'd like to share, any other funny stories or anything?
I don't know. So like I said, I'm originally from Chicago. Moved out here about 3 years ago, just trying to get away from the cold weather. But I've been loving it out here. I love the weather. I love the people. So
nice. Well, excellent. Okay, is there any questions?
So are you thinking of automating it eventually, where you don't have to manually do it?
We haven't talked about it yet. I don't know. How do you feel about that, Joe? Like even making it even more automated? It seems it'd be pricey.
I have some ideas I haven't talked about yet. Yeah.
Nice. Yeah, the one that scares me the most, like, and I agree. At some point, we're going to have to get to that. Like, our most popular board right now, we know it's going to be because we have order right now for thousands of them. Is our new inductive switch, and the first order we're going to do is 8,000 of those. And there's a processor on that needs to be programmed. Because it's an inductive switch, when a ball's nearby, each one is going to have a different tolerance on what it's going to show as its default value. So we have to program it. We have to read what we call the noise floor. How much noise is this particular sensor seeing? And what is it going to use for a detection threshold? Because some of these are going to make it, and some of these are going to have to be reworked. So when we originally did it, I think I have that board here. We were doing a board, was this 10 or 12? I could probably add up in my mind. I was at 1, 2, 3, 4, 10. So we were trying to do a 10-up panel. So we would be able to put this in a test fixture and do 10 at a time, but it kind of overdid the size of our boards. So we actually are going to do this now as an 8-up panel. And this is the actual test board for that, so you can kind of maybe see the shapes on there for the 8-up panel that's going to go on there. So even so, at 8 per panel, that's still 1,000 boards that have to be handled. So the cycle time comes, really into play. And so if we can't get the cycle time down below maybe 10 seconds to do all these, or 30 seconds on the outskirts, you're going to be wasting a whole day just doing all these. So yeah, I mean, at some point in time, I think we're going to have to do that. Any other questions? All right, well, thank you everyone for coming, and if you want to come look at this after, please come up and maybe ask some then and take a look at these. Thank you. It is now. Why do you want to tell me something? Okay, this oh my gosh, so much better now. So yeah, the main gain was messed with. So, okay, now we know.